Hello, everybody. I'm so glad you guys could make it to this Goddard Engage session in virtual space and virtual time. There are a lot of people who had planned to go down to South America, to Chile, to Argentina to see this eclipse. And with the posture we're in now with COVID, none of the researchers and even just the viewers could make it this time around. So we have been working to get feeds that we can see up here. NASA has included some on their NASA TV show, and we wanted to take advantage of what we can actually do in a virtual space and show it to those people at Goddard who wanted to take a look. What we have set up for you today is a feed pulling in from Argentina, from a telescope that is specifically calibrated to be able to see the sun from the ground. Normally this is so bright that, it would totally you'd be unable to see it through the telescope. This is calibrated to do that well. We will watch that video, but you will also have two scientists from Goddard here to sort of narrate it and tell you what they're seeing, as well as talk a little bit about the work they do that is relevant to what we're seeing here. To tee that up, I am going to introduce Nicki Viall. She is a solar scientist in our heliophysics division. She is more focused on studying the sun and what is going on there. And we also have Eric Christian, who is another scientist in our heliophysics division, and he focuses a little bit more on what the sun is sending out and what space is like outside, in between the planets, as well as even further sometimes. He studies that too. So they're going to talk a little bit about how NASA studies the sun, why we're interested, and give you a bit of a tour of this eclipse. There are questions, you can put them in the chat, people can answer, they'll be answering questions, and we're going to keep it nice and informal today, but hope you get a chance to see this eclipse from afar and learn something. Thanks.
All right. Well, I guess it's our turn, Eric. Yeah, we're really excited about looking at the eclipse, even though we don't get to be there in person, getting to watch the live stream and talk about how excited we are about the sun and the corona and everything going on.
Yeah, this is going to be exciting. I've seen in person 3 total solar eclipses. Nicki, how many have you seen?
Just one. So the 2017 eclipse, the one that came across the continental United States, that was my first time seeing one live, and I got to be on location in Portland, Oregon for that one. So that one was just amazing.
Yes, so I saw that one from Casper, Wyoming, and have seen 2 others, one from Micronesia and one from the Gobi Desert in China. So all with the Exploratorium Science Museum in San Francisco. So these things are really exciting in person, but even on video, they're just amazing to see. It's tremendously lucky that we have a moon that's almost exactly the same angular size as the sun is. That's phenomenally lucky. And so we get to see something that is astounding. It's the corona of the sun seen from the ground. It's just amazing.
Yeah, so the corona, that's the atmosphere of the sun, and it's several hundred times hotter than the photosphere of the sun, the visible surface of the sun. And what we're seeing right now is the photosphere, but viewed through a special lens, this because you can't actually look at the photosphere with your naked eye. But they're looking at it through a special lens, and you can already see that the moon has partially come across the disk of the sun and partially blocked out the photosphere, but we have to wait for it to totally block out the photosphere to see the atmosphere of the sun.
Right. The corona, even though it's much hotter, because it's not dense, there's not very much of it there, it's not anywhere near as bright as the surface, the photosphere of the sun. And so only by it's like trying to see a firefly that's up in a spotlight. You can't see something dim when there's something really bright behind it. And so only when the moon blocks off the really brighter light from the sun can you see the corona.
Yeah, and the corona is so interesting because it's extremely hot, and so it is accelerated to very fast speeds and flows away from the sun. It's not gravitationally bound to the sun. So that hot atmosphere flows away from the sun, fills our solar system with plasma, with protons, electrons, and other elements. We call that the solar wind, and it bombards all of the planets and keeps going out to the edge of our heliosphere.
Yep, it carries along a magnetic field with it. And the magnetic field and the plasma has actually blown a bubble in interstellar space. So our whole solar system, this goes out beyond the orbit of Pluto. We actually have formed a bubble that protects us in many ways from these things called galactic cosmic rays, which is one of the things I study, particles moving at almost the speed of light, subatomic particles. And I study not only the solar wind and the solar energetic particles coming from the sun, I study the entire heliosphere. And it's really neat to see structures out beyond all of the known planets that we can study from Earth. It's really fascinating.
Yeah, and we have other missions to study the solar wind and the solar corona. Parker Solar Probe is flying through the outer stretches of the solar corona. I forget when the most recent pass was, but it has passed several times.
Yep. It's starting its 7th orbit. It's right now near the distance of the Venus orbit. And so it's getting ready to head back in for its next close approach to the sun in January. I work on the Parker Solar Probe. It was named after a living scientist, Eugene Parker, who was the first person who determined the theory of the solar wind before there were any spacecraft. That was back in the 1950s. And he's still alive and still pretty active. And so, it was very fitting that Parker Solar Probe get named for him, because he really is the start of solar wind physics here on the planet. So,
yeah, Parker Solar Probe is so fascinating. It has the in situ instruments, which means that it measures the plasma and the magnetic field where the spacecraft is, but then it also has a camera that looks in white light, just like what we're about to see with the eclipse. So it has an instrument called WHISPER that looks in white light at this outer corona, and it's similar to what we're going to see here from the ground. And that NASA has other instruments that also look in white light on other spacecrafts. We call those coronagraphs, where we sort of try to mimic this total solar eclipse, but from space, so that we can do it all the time and block out the photosphere and study the corona more than just when the moon happens to line up, but on a regular basis.
Yeah, so Parker Solar Probe dips into the part of the corona that you actually the very edge of the corona that you can see with your naked eye during a total solar eclipse. That's how close it's eventually going to get to the sun. But we're using Venus to circle in closer and closer over a number of years. And so even though we're on our 7th orbit, it's not until about the 21st orbit that we'll get into 10 solar radii, less than 4 million miles from the surface of the sun. This is already, though, has gotten closer than any other spacecraft has ever gotten. And we're learning a tremendous amount about why the solar wind gets accelerated up to 1 million miles an hour, why the corona is so much hotter than the surface of the sun, and how solar energetic particles, these particles coming from the sun moving at almost the speed of light, get accelerated. This is a really exciting mission.
Yeah, it's cool just from a fundamental physics perspective. These are phenomena that we can't simulate here on Earth, and the sun is making all of these really cool it's a cool plasma accelerator, and it makes this very hot plasma and these magnetic explosions, and from the magnetic fields on the sun, we call those coronal mass ejections, and there can be particle energization with it. That's all just really cool physics to study, but it's also important to understand for protecting our spacecraft and protecting astronauts that are out in the space environment. Being able to predict the radiation that they're going to experience is really important for astronaut safety.
Yep, so we got a question asking about the peak of the eclipse. So it doesn't really have so much a peak as it'll last for as long as the moon is completely blocking the sun. And that starts a couple minutes after 11 o'clock Eastern time and goes until I think 11:08. So this is a relatively long eclipse. Eclipses can be really short. This one is, I think, 5 minutes or so long. So it should be, really impressive. One of the exciting things about this eclipse is that there are a number of active regions on the sun. And so the 3 eclipses I've seen live have all been pretty quiet sun, and they look like a magnetic dipole. So it's a very simple corona that you see when the sun is quiet. Why don't you tell us about what we're expecting to see this time, Nicki?
Yeah, so active regions, we call them active regions because they're magnetically active. They have concentrations of magnetic field in them. And these are associated with intense X-rays and ultraviolet light. So when we look at the sun in those wavelengths, we see extra radiation associated with these. These are also the regions that ultimately can create these big solar explosions, the coronal mass ejections and the solar flares. So the active regions, because the plasma can't cross magnetic field lines and the magnetic field controls then the shape of the corona. So when these pockets of intense magnetic field show up on the sun as the solar cycle rises, then we get these really complex shapes in the corona. And that's today we know from our Solar Dynamics Observatory that there are active regions on the limb of the sun, on the side of the sun. And so we expect that the white light will also have very interesting shapes associated with that once we get to see that.
One of the things I've always found fun is that there's a nice demo that you can do where you take iron filings, and sometimes they're held in a container and stuff, with in a permanent magnet, and you can actually see the iron filings will line up with the magnetic field from that little magnet. And you can do that on your desk. What we're seeing on this plasma, which is glowing, following the magnetic field lines of the sun, the exact same way the iron filings do on your little tabletop demo, except we're seeing streamers and loops that are bigger than the Earth. It's really fantastic that the same effect can be everywhere from hand-sized to, as large as the sun.
Yeah, it's just amazing how big these structures stretch out into the solar system. And then there's this feedback. Low to the sun, the magnetic field energy and pressure really dominates, and so the magnetic field is holding that plasma in place. And then further out, the plasma starts to get enough energy that it blows open the magnetic fields, and that's what forms our solar wind and ultimately our heliosphere. So that they have different energies, and the magnetic field holds everything in close, and then there's this different feedback between the different energies. It's really cool to watch.
Mm-hmm. So we've just gotten a question from David. Is there a difference between an eclipse during the summer and one during the winter? No. The answer is, although it turns out that there are 2 seasons for solar eclipses every year. And you can have solar eclipses somewhere on the planet each time, but actually only a half of them or so. So you only typically have 1 total solar eclipse a year. But there are 2 times when the orbit of the moon, which is in a plane that's tilted to the orbit of the Earth around the sun, only when those 2 planes line up can you actually get a total solar eclipse. And so that's why the total solar eclipses are clustered in 2 seasons every year. Mm-hmm.
Yeah, another interesting thing is because this one's viewed from the southern hemisphere, their point of view is going to be about 170, 160 degrees tilted relative to what our spacecrafts, which align with the solar rotational axis. So it'll be, our view from the spacecraft will be about 160 degrees tilted from what they're going to see from the ground and what we're seeing on this live stream here.
Mm-hmm. So, but we can figure that the poles, so because the moon is moving perpendicular to the poles roughly, we can see that the poles are going to be at 1:30 and 7:30 on the clock, on a clock dial from this image. Mm-hmm. So, and you're saying that the North Pole will actually be pointing down probably on this image?
That's right. So what our feeds will pull down from SOHO, for example, which is looking at, that'll have solar north aligned. And if you're looking from the ground from Chile, you're faced the other direction, and it's about 160 degrees different. So when you're comparing what we see on the ground with what our NASA spacecraft observe, they'll be different. You have to rotate them to get them back in alignment.
Mm-hmm. So I've just been told that the times I had were actually for a Chilean feed that we thought we were going to get originally, and for the Argentinian feed of the telescope that we're seeing here, the eclipse will start at about 11:05 and end at 11:08. That's a better timing for the eclipse, because the shadow of the moon moves across the Earth at a couple thousand miles an hour, and so even though it's the same eclipse, the time of the eclipse depends upon where you are along the track.
Yeah, exactly. And in fact, most of the eclipse is going to be over the ocean and not visible from land anyway, and that happens most of the time. I mean, most of the total solar eclipses happen over the ocean and don't happen where people actually live and can view them. So it's so cool when we actually get to actually be able to see one in person.
Mm-hmm. Yep, that's why for the one total solar eclipse, I went to Micronesia, because there was only two parts of land that it really went over, a little part of Indonesia and this one pretty remote atoll in Micronesia, and it was a blast. You know, the population of about 350 people on the atoll, and very friendly, and that was pretty amazing.
Yeah, and then the 2017 eclipse across America, I remember it took about 90 minutes to get from where I was in Portland to where the final feed was in on the East Coast. And then the next one that's going to come across continental United States is the 2024 eclipse. And that starts up in Texas and then kind of cuts up kind of to the northeast and goes out New England. So that is another really exciting one where a lot of the continental United States will get to see a total solar eclipse.
Yeah, the 2017 one was nice because every single part of the continental U.S. was in partial eclipse, and most people could travel to the total solar eclipse if they needed to.
Oh, yes. Parker Solar Probe is essentially observing only in the ecliptic, which is where the Earth orbits and the planets orbit. Are we missing anything by not looking over the solar poles? Absolutely. In fact, the predictions made for what the coronal looks like right now, one of the big uncertainties is all of the magnetic field that is coming out of the poles of the sun that we actually cannot measure right now. So Solar Orbiter is going to come up, I think, about 30 degrees using Venus assists. And so it'll have a glimpse of the sun. There's also a mission called Solaris that was selected for a Phase A study, so it's being studied right now. But the idea with Solaris is that it is also going to use a gravity assist to get over the poles and look down on the poles, the magnetic field, and how this white light corona also looks totally different when we're looking down from above as opposed to looking from the side.
Yep, I think it's important to mention that Solar Orbiter is led by our partners at the European Space Agency, although NASA does have a part of it. But the combination of Solar Orbiter and Solar Probe over the next 5 years or so is going to be really exciting. These are two complementary spacecraft that are going to increase our knowledge of the sun tremendously and already have started.
Yeah, and they both have white light instrumentation that can look at the same kind of thing that we're about to see during totality.
Yep. And there's only been one other spacecraft that's gone over the poles of the sun, but it didn't have any imagers. That was Ulysses 20 years ago. So we have gone over the poles with what Nicki said were in situ particles that measure particles and fields and stuff, but we've never had a camera looking down or up on the poles of the sun until Solar Orbiter gets there.
Yep. All right, we have another question. It says, what determines the length of the solar eclipse? Well, whole solar eclipse, it has to do with the alignment of the moon, the Earth, moon, and the sun, and how much of the moon blocks out. And I think it's just sometimes. Yeah, go ahead, Eric.
Yeah, so if you take the disk of the moon, you can get total solar eclipses. The moon is slightly larger than the sun, and you can get total solar eclipses, for a range of differences in height between the two. The longest ones are when it's an exact hit, where the center of the moon crosses the center of the sun, and that gives you your longest eclipses. But if the moon is offset a little bit, you can still get a total eclipse, but the more offset it is, the less time you'll have a total solar eclipse. So it's just a luck of timing between when the moon actually crosses in front of the sun.
Yeah. Let's see, I think we're probably about 15 minutes away. So it's getting close. You can see in the feed that the moon is starting to line up, but it's still, if you were there in person, it would still be extremely bright. Even though the moon is crossing out blocking most of the sun, it's still, with the naked eye, you wouldn't even be able to tell. It would still be too bright to look at.
But it is fun to look around when you actually get to totality. You can't actually look at the sun even with a little bit of a crescent, unless you're wearing eclipse glasses, which are specially designed to block most of the light of the sun. But with a minute or two to spare, it will start getting dimmer.
Yeah.
And when you get to totality, it's still relatively bright, like, full moon type brightness. But it's this really weird light. After my first eclipse, I described it like the old B movies where they filmed during the day and they put the night filter on, but you still get really sharp shadows and stuff. And you still get shadows but it's this very weird light. And you can also get, depending upon where you're situated and whether you can see the horizon, you can actually get at like 360 degrees of dawn. Yeah. All the way around on the horizon, because the shadow of the moon doesn't go horizon to horizon if you're in the right spot. So
yeah, it almost feels like dawn or dusk, except that's not even quite right either, because it just it's sort of I had kind of a visceral, like, something doesn't feel quite right, this is definitely different. And it's kind of even hard to explain if you haven't witnessed it in person. I had a similar experience when I saw the aurora borealis, the northern lights, in person. It's sort of like your intuition is that that's not what things are supposed to look like. And it just feels sort of amazing, but also surreal almost.
Yeah, people should try once in their life to see a total solar eclipse, and also should try to see the aurora. It's really amazing. I've seen it a number of times from northern Canada, but one time there was a storm going on, and we just spent most of the night lying back on the hood of a car, looking up at the stars, and fast moving, multiple colors, ribbons. I mean, it's just it's nature's artwork. It's just really amazing.
Yeah. So the northern lights are caused by these big
exactly
solar explosions. Yeah, these big coronal mass ejections, and all of the energy and the magnetic field that they send out. When that gets to our Earth and interacts with our magnetic field, and the storage and release of that energy with our magnetic field is what accelerates the particles and makes these beautiful northern lights.
Yeah, because the accelerated particles come into the upper atmosphere where the magnetic field of the Earth, the field lines, just like on the sun, you get these field lines that make a dipole shape. And where they come into the atmosphere near the poles, those accelerated particles come down and actually cause the gas of the atmosphere at high altitudes to glow, just like in a neon tube, light, fluorescent light. So.
Yeah, and depending on how the energy comes to the Earth and how it interacts with the Earth, you can get little aurora, you can get bigger aurora, they can last for a long time. There's all this movement of the aurora as the Earth's magnetic field reconfigures itself in response to this energy. It's really amazing to watch.
And you get different colors from the different energies and the different gases in the Earth's atmosphere too.
Yeah, I think we saw a little bit of purple when I saw the one in person. That's kind of more difficult to see. The green is real common, and then the red is the kind when the aurora come down south. That's the kind that you can even get down kind of in the continental United States. That's the kind that'll come down here.
Yep. Yeah, we saw actually things that looked like the old ribbon candy that had green, white, and red, in fast-moving ribbons across the sky. It was pretty impressive.
Yeah, they're just amazing. All right, so I think we're about 10 minutes away. It's getting close. It's getting close. Yeah. When you're looking at these partial eclipses, either on the way to total solar eclipse or if you're in a region where it just never reaches totality, you can see this pattern of the moon taking a bite out of the sun with a pinhole camera, or even, I remember you can even just use your hands and stand with the sun at your back and put your hands in the way, and you'll make an image on the ground of the little crescents of the moon blocking out the sun. I have a picture of doing that at the 2017 eclipse.
Okay, so we just got a question about when astronauts go to Mars, do you think they'll be able to observe eclipses from there? No, the two moons of Mars are way too small. You'd have to be sort of nestled right up against them, and they're not round, so, but it's only here on Earth with the moon at exactly the right size and distance that we get to see total solar eclipses. You won't see them once you get out beyond the Earth's orbit.
Yeah, and in fact, the eclipses used to look different, and they will continue to look different because the moon used to be closer to the Earth, and so then that was a different, it made a different angular, took up a different amount of the sky from the Earth's perspective. And then as the moon spirals away, eventually we're not going to have total solar eclipses anymore because it just won't be close enough to us to block out the sun. So that's really amazing too, that the eclipse, sort of what eclipses looked like and how long they would last and so forth, was different earlier in time.
So as we're getting close to totality, why don't we tell people what to expect? There's some really interesting things, Bailey's bead, the diamond ring, we might see prominences. Why don't you tell us what we're going to see as we get to totality?
Yeah, I mean, the biggest thing, of course, will be all the structure and the white light. There's like a flash right before, I forget what is the flash called? The diamond ring?
The diamond ring, yep.
Yeah,
as the
right.
last bit of bright sun disappears behind the moon.
So that's a pretty cool phenomena. And then it all depends on exactly what the sun has decided to do today with its magnetic fields. Sometimes what can happen is the magnetic fields will hold up this colder prominence material is what we called it. It's colder material that it holds up in the corona. And because it's colder, it'll actually look red. It'll look different if the sun is doing that this particular time. It doesn't always happen. You have to have the special magnetic configuration and the special formation of this colder plasma up in the corona. So that's pretty cool if we can see that. It'll look, like I said, it'll be red as opposed to the white light, which will be most of what we see in the corona.
And yeah, and there's also a thing called Bailey's beads that comes before the diamond ring, which is actually the moon is not flat. It has mountains. And so the fact that the edge of the moon, you can't see. I mean, if you look at the picture now, and they've now just zoomed in, so good timing, the edge of the moon looks pretty much circular, but there are actually features along that edge. And when we get to the very, very last seconds before it closes up the moon, you'll be actually able to see those features because the sun will be peeking out between the valleys but blocked at the mountains. And so that's called Bailey's beads. That's, really fun. Yeah, we might see prominences, red prominences and stuff. And so, and then the white light corona. It's getting close now.
Yeah, super close. Yeah, it's going to be really exciting to see. Some of our colleagues have made predictions about exactly what the corona might look like based off of these magnetic fields. But not only can't we see the poles and the magnetic fields coming from there, we also can't see the backside of the sun. So if there's active regions on the backside of the sun that contribute to the shape of the corona and these concentrations of magnetic field, we actually can't see them right now. So we're guessing based off of what the sun looked like, a week or two ago, what might probably still be on the backside of the sun.
Yep, but the funny thing is that a number of years ago we couldn't see the backside because we had the stereo mission. Now we can see more than half the sun because the one spacecraft, Stereo A, is still working and is about 50 or 60 degrees away from the Earth, and so sees a different part of the sun than the Earth does. But Stereo A and B both went in behind the sun, and for a number of years there, as they were on the back side, between the two of them, we could actually see the entire sun for the first time. But Stereo B is no longer working, and Stereo A is heading back around towards the Earth, so we can't do that right now. It'll be another 15 years before Stereo A gets back in position to see the full backside of the sun. But
we hope it's still on then. It's still looking.
Spacecraft can work for a long time. The two Voyagers have worked for 43 years. So.
Yep. Yeah, Stereo also has this artificial eclipse called a coronagraph. So it also sees the corona, and it also has a special instrument that also looks in white light, but it looks off to the side so we can see the solar wind as it flows out and fills the solar system and ultimately hits the Earth. And we can see some of these coronal mass ejections, these explosions, as they propagate to the Earth too. Because Stereo right now is on the side, it can look and see the stuff that then shoots off the side of the sun from Stereo's perspective and then hits the Earth. So that's a really cool different perspective.
And that's a similar instrument to the one that's on Parker Solar Probe that looks off to the side.
That's right. And Solar Orbiter also has both
that's right.
the
coronagraph, yes.
Yep, and the off to the side view, the solar wind view.
So we're getting close now. Just a little crescent of the sun left.
Yeah. Yeah, it's amazing. You can actually see, now that they're zoomed in, that the moon, though slowly, is moving across the sun. You can tell that it's about there.
Yep. So Stan has asked that, is it true that total solar eclipses won't be a thing in the future since the moon is moving away from the Earth? The answer is yes, although it's many millions of years before the moon moves far enough away that, but eclipses will get less common and shorter as that time goes on. But there'll be a time like 100 million years from now or something. I mean, I don't remember the exact number, but there'll be a time where there won't be any more total solar eclipses. Okay, we're getting really close now. You're going to see Baily's beads in a minute, and then you're going to see the diamond ring, and then they hopefully will cut to a different camera that can show us the white light corona.
Yeah.
And I wish they didn't have the bar blocking part of it. So there you can see the structure at the edge that'll make the Baily's beads.
Yeah.
Those are actually mountains on the moon.
Yeah, it's so neat. The LRO spacecraft has mapped out a lot of the structure on the moon too.
There's the diamond ring.
Yep.
From a different camera.
Yeah. You can see it starting.
Yep.
All right, and we're in totality.
Mm-hmm.
And I hope they zoom out so that we can see what the corona looks like.
There we go.
Yeah.
not as contorted as the predictions would indicate in that view.
No, it looks actually pretty dipolar, huh? With the
Yep.
we call those streamers, the part that's sort of at the equator where the corona seems to bulge out, because those are those long loops of field line that connect back to the sun on both sides. Whereas over the poles, yeah, go ahead.
This one looks to be tilted 90 degrees. And so where the filaments are coming out, where it looks like there's hair on the sun, those are polar plumes. And that shows where the north and the south poles are. So on this one, the streamers are going up and down, and it looks like the poles are basically 90 degrees, right?
Yeah. Yep. And it looks like there's...
Yeah, here they've gone back to the
yeah, I think they are switching back and forth.
Yep. But you can still see from the shape that the equator is the way you would expect on a map. It's roughly, horizontal on this plot, the equator of the sun, and so the poles are up and down.
Mm-hmm.
Whereas this one, the equator is up and down, and I would say the poles are left and right.
That's what it looks like to me.
Look, there's a filament in the upper right.
In the upper right, it looks like there's that prominence material, right? That red prominence material. That's it's still plasma, but it's colder than the corona, and it's suspended by magnetic field lines up in the corona, and so you get this different appearance.
Up, and now it's coming to an end. Amazingly, how fast. There's the edge of the sun peeking around again.
Yep. And those mountains.
And now you see darkness is descending.
Yeah, so now the moon's crossing out the other side.
Mm-hmm.
I remember at the 2017 eclipse, when we were there, you get cold during totality because it blocks enough of the sun that you actually feel the temperature actually decreases.
Yep. Depending upon the area, the temperature can drop by a number of degrees, like 3 degrees and stuff. And so yeah, it's.
They had a lot of experiments during the 2017 eclipse looking at the atmospheric response, both the temperature, but also waves and things like that, and how the atmosphere responded to the input from the sun.
So there's this interesting effect that you can get where you can see shadow waves sort of moving across the ground. Only happens in certain atmospheric conditions, but and there have been, actually people who don't believe that it happens, but there are enough sightings that you can actually see maybe interference patterns coming, from the sun as the shadow at the very edges of the eclipses. But I've never seen it. So
yeah, the eclipse or the sun, of course, what we're used to is how it affects. We feel hot on a hot day when the sun's out and bright, but the ultraviolet light also affects the ionosphere and interacts with our atmosphere that way, and other planetary atmospheres too, because it ionizes the atmosphere. Oh, Travis said he saw
them in Carbondale on the 2017 eclipse. So Carbondale, Illinois is interesting because that's where the tracks from the 2017 eclipse and the one that's coming up in 2024 cross. And so Carbondale, Illinois is going to get 2 total solar eclipses 7 years apart. Whereas normally, if you just stand on the same spot on the planet, it's roughly 300 years in between total solar eclipses. That's why we have to travel to see them, usually. That's really cool that Illinois gets that. Also, just that the United States is going to have these
these two eclipses, two total solar eclipses, close enough together that people will, remember getting to go to both.
Yep.
And the likelihood of having a location that isn't totally clouded over, because that's the other thing, of course, that we experienced this morning, is that you get everything all set up to view the total solar eclipse, and then the weather doesn't cooperate, and if it's cloudy or rainy, then you can't see the total solar eclipse.
Mm-hmm. Yep, and so the professional eclipse chasers look at where the lowest likelihood of clouds and rain are, and try to find where on the track you can go to have a small, like deserts are good because less chance of clouds and stuff. But Seattle actually got to see the eclipse, but people were worried about the rain of Seattle. But it is still a probability. Certainly, I've been lucky and gotten 3 for 3, but lots of people have taken, trips that, planned a year in advance and taken trips to see the total solar eclipse and not been able to see it because of clouds.
Yeah. So. Yeah. Well, I'm super excited actually now to see what we saw in the spacecraft and how that matches with the total solar eclipse, because our artificial eclipses that we make in space, we can't quite do as well with the scattered light from the sun as the moon does. The moon is the perfect, it perfectly blocks out that photosphere of the sun, but and so you can see all the way down to that photosphere and how the corona maps down and the connection between the solar system and down to the sun. But our artificial eclipses don't go that low in our instrumentation.
Yep, and it has to do with how close what's blocking the sun is to the telescope. The further you can put the blocker, but for coronagraphs, you can't make something that's where the thing that's blocking you is on the same spacecraft and all that far away. There's a finite size to the spacecraft that you can build. Whereas the moon at 240,000 miles away, you don't get much diffraction around the edges. And so that's why you can see a lot more of the corona. We got a question. Is there a physical reason the moon is roughly the same angular size as the sun, or is it just luck? Just luck. If you look at the moons in the solar system alone, which is our best, which is the only other data we have, our moon is basically the only one that is exactly the right size to give you a total solar eclipse.
But it's also a bit of luck in the sense of how close it is to the Earth, because it used to block out more, and then you didn't actually get to see quite as low down on the sun. And then, of course, as it spirals away, it'll block out less. Mm-hmm. Okay, we have another question. In which city will peak totality be during the 2024 eclipse?
So I don't remember where the longest eclipse will be. I would have to check a map, but the entire track of totality, so you'll get to see totality in a track that goes all the way from the southwest to New England across the U.S. So and the differences in the length of the eclipse on different parts of that path won't be that different, but there will be some point where you get the longest possible eclipse.
Yeah, I seem to recall it was a bit longer, more like 3 or 4 minutes of eclipse, maybe even 5.
Mexico.
Okay.
NASA Durango, Mexico is where the longest total eclipse will be in 2024.
4 minutes and 28 seconds, yeah. Yeah, that's really cool. We, the sun doesn't do a whole lot in just a couple of minutes. So during the 2017 eclipse, they tried to piece together all of the eclipses from all over the country, because that took about 90 minutes. And so then you could see a little bit of evolution on the sun and some of the activity that the sun has. The sun evolves sort of on all scales. The long scale, the 11-year solar cycle, is how long it takes these active regions, these magnetic fields, to pop up and evolve, and then the sun actually switches its whole polarity, and then it goes into a quiet time where we don't have as many of these active regions. But then the sun also evolves and has dynamics on year timescales, month timescales, week timescales, and even minutes. So it's really cool to get to see all of these different timescales.
Yes, so in 1860, there's actually a drawing that indicates that they were, actually there's a number of drawings where they were lucky enough to get a coronal mass ejection going off during the total solar eclipse. And so you can see this bubble of hot plasma in the drawings that people did of the corona at the time, right? 1860, pencil drawings of the eclipse. So that was that must have been pretty wild.
Yeah, that must have been amazing to see. I can't imagine getting to see that. That would have been really cool.
And they didn't know what it was. There was no such thing as a coronal mass ejection back in 1860.
It's been pretty recently that we figured out that these explosions on the sun actually are the same thing that are causing these dynamics on the Earth. There was a lot of guessing that probably that's what it was, but it took a long time to actually piece together all the observations to prove that. It was pretty cool.
Mm-hmm. Yeah, I mean, it was only the year before that, in 1859, that the Carrington event, the largest solar flare of modern ages, went off. And a couple days later, as the magnetic storm hit the Earth, it actually fried telegraph lines and pretty amazing. And that was one of the first times where Carrington actually saw the flare in white light by looking through a filter at the sun when it happened, and was, and they matched it up to the storm, the geomagnetic storm that hit a couple days later.
And it's actually rare to see them in white light because it has to be pretty big for it to have that. It has to have enough energy to get into the white light. Usually we see them in X-rays and ultraviolet because they don't penetrate that far. So we have, a comment from Vanessa. I was in Aruba in the February 1998 eclipse. She saw 6 total eclipses and saw the shadow bands multiple times. There's a hybrid eclipse in 2023, not a total or annular. What does a hybrid eclipse mean?
A hybrid eclipse means that it's annular over part of the track and total over another part of the track. So you can have an eclipse. Annular eclipse is where the moon is far enough away, because the orbit of the moon is an eclipse. An annular eclipse happens when the moon is far enough away from the Earth that it's actually slightly smaller than the disk of the sun. And like I said, so a hybrid, but that size of the shadow actually depends upon, whether it's a direct hit on the Earth, the front of the Earth is closest to the moon, and the back part is a radius further away from the moon, and that's enough to make a difference in some eclipses where you get annular over some parts of the track and total over other parts of the track. Mm-hmm.
Let's see, Marcel says, is the camera in Argentina in some kind of observatory? Is there a spacecraft? We're looking into that. It's definitely from the ground, is definitely the feed we're looking at.
Yeah, spacecraft don't have a province, and this is from Nicki province in Argentina.
Yeah, also as we said, we don't get from the spacecraft, we don't get to have a giant moon blocking.
Yep. So in low Earth orbit, you can still get total solar eclipses, but further out, from geostationary and stuff, that you wouldn't ever see an eclipse, except you can see the shadow of the moon on the Earth. And there are images that are really fun. The first time I saw that was so cool. And we've had now for years Discover out at L1, which is constantly taking a movie of the Earth, and you can see the shadow of the moon pass over the Earth, and that's always fun to watch. You should look on the web for that if you're interested.
Yeah, that's pretty cool. I also remember we had airplanes taking pictures for the 2017 eclipse, so we had observations from airplanes looking.
And balloons.
Mm-hmm.
Yep. So what's nice about balloons is that you can get up above the clouds, and so don't have to worry about it being rainy and foggy and like it was in Chile this time around. So
yeah.
okay, so we're heading now to more and more of the sun being visible. People are welcome to still ask questions.
Yeah, the partial phase of
Okay.
the eclipse lasts for a very long time relative to totality.
Yep.
Let's see, it's
Told
pronounced Nuken
Neuquén province. Yep.
in Argentina. Yeah, I was thinking, how would astronauts aboard the ISS see the eclipse away from Earth's atmosphere? I think that's what you were saying, Eric, from Leo. You can see the eclipses, and then you're above the atmosphere, so you don't have...
But their orbit would have to be right. They'd have to be inside the shadow. And
Exactly.
so it's not clear. I don't think this time around they actually could see the eclipse. I know they couldn't in 2017, but they may be able to see the shadow looking down. But the eclipse is, the shadow is pretty small, and if the orbit of the space station doesn't go through that shadow, you won't see it from the space station.
That's right. Yeah, it's a very, very, very small percentage of the Earth's surface that gets totality. And
Yep.
And that's why we have the spacecraft doing their best to study the solar corona all the rest of the time, because it's so rare that we get these total solar eclipses and that everything cooperates with the weather and being able to see them.
Yes, SOHO has given us a lot of what we know with its decades of coronagraph, same coronagraph, and there are newer ones up now, but SOHO, which again is one of these missions that has lasted for decades, despite having some problems, and they've recovered it, and it's just amazing the engineering that's done on some of these spacecraft and make them last so long.
Yeah, SOHO was another collaboration with ESA, with European Space Agency, and they just celebrated, SOHO just celebrated its 25th year anniversary. See, Karen says, I was in Wyoming in 2017, and your skin looks gray in color, and all the birds and the animals got quiet and silent while in totality.
Yeah, when I was in Micronesia, there were these things called fairy terns, these white seabirds, and they started doing their morning dance as it came out of totality, the spiraling dance where they all came out of the trees and started doing their morning dance because it had gotten dark only for a couple minutes and then gotten light again.
Yeah, the animals definitely respond to the eclipse. Let's see, we have another question. How were they able to see coronal activity in the 1860s? They had the ability to measure the magnetic field or infer the magnetic field from the white light observations of the photosphere. They're called sunspots when you look in white light, and it's because the energy balance between the magnetic field and the photosphere actually makes it colder, so it's darker, these concentrations of magnetic field. So they had that, they knew that, and then otherwise it was these total solar eclipses was just about the best way to see the corona.
Yep, that was the way. They didn't actually know very much about the corona except from total solar eclipses. So let's see, hypothetically possible for a total solar eclipse and a Venus transit to happen at the same time. Well, then the moon would block the Venus transit.
Right.
That wouldn't be very interesting, but let's see, is there any reason why? I would have to see the tilt of Venus versus the tilt of the moon, but there's precession and stuff, so I would think in millions of years.
Yeah, I would think ever.
Yeah, but they're both rare events. I mean, total solar eclipses happen only once a year. Venus transits happen even less. So to get the timing exactly right for a couple minute, sort of things, two of them is a real long shot. I'm not expecting to see it.
And then, as you said, to actually see the Venus transit, then actually you would want to look with something like one of our spacecraft telescopes,
Yep.
so that actually you could see Venus coming across the face of the sun. SDO, I believe, caught the last Venus transit. Yes. And there's been at least a couple Mercury transits that Solar Dynamics Observatory also caught.
Yep.
They're just cool to watch, but we also use them to help calibrate our instrumentation when the planets cross in front. And we help use them to quantify the scattered light in our instruments.
Okay, what's the story with nanoflares from Billy? You want to take that one, Nicki?
Yeah, so nanoflares are one of the things I studied. These nanoflares, we believe, as the name implies, are sort of little flares, little solar flares, little magnetic explosions, and we believe they're helping, that they're playing a role in heating the corona, making it, several hundred times hotter than the photosphere below it, and providing the energy that then ultimately can help make the solar wind, make the plasma so hot and energetic that it flows outwards into the solar system. So nanoflare was coined because the energy that these must have is about 10 to the 9 times smaller than one of the big canonical solar flares that's associated with these coronal mass ejections and the aurora borealis once they get to the Earth and so forth. And they're too small to see directly with current instrumentation, but we've seen evidence of how they affect the plasma on the sun with instruments like Solar Dynamics Observatory. All right, well, I think we're getting close to the end. I don't know if there are any final questions or any words of wisdom, Eric?
Nope. This was fun. It's better in person. And like I said, I recommend that everyone, especially if you're interested in science and you should see one total solar eclipse in your life. And the 2024 one, which is going to cut across the United States again, is one you should definitely make plans for.
Yeah.
So.
Comes up through Texas and goes out New England, and there's a lot of places you can go see it. So definitely make plans to go now to go see the 2024 eclipse. And does NASA have a plan to engage the public in the 2024 eclipse like it did in 2017? Yeah, I believe there are plans already.
Yep. I mean, that's one of the reasons why NASA set up at Carbondale, Illinois, because that's where they're going to go back. That's one of the places they're going to be back in 2024. We also got a follow-on from Billy on what causes nanoflares.
We believe that nanoflares are caused by magnetic reconnection, where the stored energy of the magnetic fields releases, and that energizes the plasma around it. So the stresses from underneath the photosphere, as the magnetic fields get stirred up, create stress in the magnetic field, and it gets released.
Yep. So in that, the magnetic field lines, which normally are sort of constant and just wiggle and move around, but in magnetic reconnection, they actually break and reform in a different way. And so it's a really fun thing. And NASA has a mission with 4 satellites called the Magnetospheric Multiscale Mission that's in Earth orbit, for the first time actually trying to fly through reconnection regions and understand what's happening. So
yeah, a lot of cool stuff being seen.
Okay, well, I think we're gonna, I guess, close it out. Looks like about a quarter of the sun, or maybe half the area now is back visible, and it's been fun.
Yeah, this was super
excited.
cool.
Yep.
Cool to see it, better to see it in person.
Yes.
Yep.
So, great working with you, Nicki.
Yeah, you too, Eric.
Okay.
Thanks, everyone.
Thank you.